Alright, what we're going to discuss now is something called a primary standard solution. Okay, now any standard solution is a solution that has an accurately known concentration. Okay, now this phrase accurately known is really crucial here. Now when we say accurately known, we mean we know the concentration uh, to we're confident in our number for the concentration, and we know it to 3 or 4 decimal places. Okay, we know it to a few decimal places. Okay, so quite accurately known. Now, basically, a primary standard solution is a certain type of standard solution, okay, that's created directly from dissolving a substance in a beaker. So we've got a bit of substance here, okay, and we've got not a beaker, we've got a volumetric flask. It's a rough picture of a volumetric flask. Okay, so all we do to create a primary standard solution, we get this substance here, we put it in a flask. Okay, we fill the flask up to this line here. Okay, and so that we know exactly how much solution is in there. Okay, and then we dissolve it all up, shake it all up, and then we have an accurately known concentration. Okay, now but first what I'm going to talk about is this substance here. Okay, there are actually very specific criteria for what we can use as this substance here in order to create a primary standard solution. Okay, now what we call this substance is a primary standard, interestingly enough. Okay, primary standard is basically a substance that we can weigh and therefore know the number of mole of the substance that we have weighed to a very high degree of accuracy. Okay, so there are certain criteria for something to be classified as a primary standard. Okay, we can't just use any substance. Okay, because a lot of substances are inherently impure. Okay, simply because they react with air or whatever, or they are difficult to obtain in a pure form. Okay, so these are the criteria here. So the first criteria is that it has to be soluble, obviously, because we're talking about creating a solution. So primary standard needs to be soluble, must be purely obtainable. Okay, so you must be able to get it in a very pure form. Okay, we must be able to obtain some of this substance in a very pure form. So we'll call it purely obtainable. Okay, it must have a known formula. So it sounds like a bit of a given, okay, but we need to make sure we know the formula of the substance if we're going to use it as a primary standard. So the substance must have a known formula. Okay, and finally, you need to be able to store it without it deteriorating or reacting with the atmosphere. Okay, because that's a big issue. If it reacts with the atmosphere, if it deteriorates, then it won't really fit many of these criteria anymore. Okay, it won't be pure anymore, and it won't have a known formula. Okay, so it must be stored. Deterioration. So it might decompose over time by itself, for example. So without deterioration or reaction with air. Okay, so when we're calculating the concentration of a solution, okay, we know that we use the formula C equals N over V. Sorry. What we're looking at is the number of mole. Okay, when we're calculating the number of mole of a substance, we use N equals M over mole mass. If we have something that's purely obtainable, basically we're making sure that when we figure out the mass of the substance that we're about to dissolve, we know the mass exactly. If it's impure, then we might have 10 grams, then this sample might weigh 10 grams, okay? However, only 9 grams of that is the substance that we want. So say we want to use sodium carbonate as our primary standard. Say we want to use sodium carbonate here, okay? And we've got 10 grams. We've got 10 grams here of sodium carbonate, okay? If it's not purely obtainable, if this isn't pure sodium carbonate, okay, then of that 10 grams, we may only in fact have 9 grams of sodium carbonate, or we may have 1 gram of something else, okay, in which case we would need to plug the number 9 into here, Okay, and on top of that, on top of having the wrong number here, we'd have some other substance, 1 gram of some other random substance being dissolved in this standard solution, okay? And that inherently has its own issues. Okay, secondly, okay, this substance has a known formula, okay? That's important, okay? So we can't have, we know the formula of this substance, okay? If we don't know the formula, if we don't know if it's sodium carbonate, or if we're not exactly sure sort of what this is, then we can't figure out the molar mass, okay? So having a known formula is important for working out the molar mass, all right? So the fact that it's pure is important to get the mass right. The fact that it has a known formula is important to get the molar mass right. Similarly, to make sure it's stored without deterioration or reaction with the air is again to make sure that the mass is right. Okay, acts with the air, then again, that might cause this 10 gram sample to become 9 gram sodium carbonate and 1 gram something else. Okay, so these are the 4 key points that we look for when we're looking for a primary standard. Okay, now another one that we can kind of throw in here. Okay, it's not as crucial, but it is kind of true. Okay, if a substance has it's not a criteria, but it's a useful property, I guess, of a primary standard for it to have a high molar mass. Okay, now all that this does basically, okay, it's almost a little bit pedantic, but if we're using a substance with a high molar mass, okay, and then we're using this equation to figure out the number of mole using this high, then any errors in the mass that may come about due to impurity or due to errors in the weighing equipment, any error in this number for mass is going to have a lesser effect on the number of mole, okay? If we have a high molar mass here, okay, the higher this number is, then the smaller this number is, then the smaller this whole fraction is, okay? And so the effect of any error in the numerator is going to be reduced by having a high denominator and having a high molar mass. Okay, so that's not really a criteria for calling something a primary standard, but it is a useful property that we may look for in a primary standard. So now we move on to how we actually create the primary standard solution like we've got up here, okay? So we know that primary standard solution, okay, we've got our primary standard here, so we'll just cordon this area off. Okay, we've got our primary standard here. We're dropping it into the volumetric flask. And what we're going to do now to ensure that this primary standard solution does in fact have an accurately known concentration. Okay, there are basically some steps we have to follow. First, what we do is we put it in. Okay, we put it into the empty flask. The next step is to fill the flask up a little bit. Say, fill it up to here. Okay, once we filled it up to there, what we do is we stopper it. Okay, and we give it a bit of a shake. Okay, we shake everything about, shake it around until this dissolves. Okay, so we fill it up just a little bit, maybe halfway, maybe 2/3 of the way to this line. Okay, on that, we fill up the rest of the way. Okay, to this line. So this line signifies that we have exactly, for example, if we have a 250 milliliter volumetric flask, then this line signifies that we have exactly 250 milliliters of solution in the flask. Okay, once we fill it up to this line. But the reason that we fill it up halfway, then shake it about until it dissolves, and then fill it up the rest of the way, is that the volume of this substance may change when it's dissolved. Okay, if we fill it all the way up to the top, and then we dissolve it, the volume of the solution may go up slightly once it's dissolved. And if it goes up slightly, if we go it all over this line, then there's no way that we can get back to the line or under the line without altering the concentration or the amount of substance. And it's all over. We can't really do a lot with it anymore. Okay, so that's the first important part of creating a primary standard solution, is that we fill it up, maybe half, maybe 2/3 of the way, then dissolve it, and then fill it up the rest of the way. The second important part is exactly what we mean when we say fill up to the line. Okay, so if we zoom in on this region here, okay, then what we have is, okay, we've got the two sides of the volumetric flask there. We've got the line, the horizontal line engraved on the flask here. Okay, and we've got the surface of the water. Okay, so if the solution is filled up to the line, then it forms this meniscus shape. Okay, we call this arc that is formed at the top of the solution. Fill up any container with solution or with water, it kind of forms this arc. Okay, the surface isn't actually flat. And so when we say fill the flask up to the line, we mean fill it up until the bottom of this meniscus arc, okay, so this point here is sitting on top of the line. Okay, so the bottom of the meniscus has to sit on the line. Okay, just like we've shown here. The bottom of that arc is sitting, I'll use a bright color. The bottom of that arc is sitting right on the line, okay? And so everything else looks like it's above the line, except the bottom of the meniscus is on the line, and that means we've filled it up the right amount. Okay, so that's kind of the process of creating a primary standard solution. We pick a primary standard based on these criteria, such that the amount of mole we have of a substance just by weighing it. Okay, and all these conditions improve the accuracy of this calculation for the number of mole. Okay, once we have a primary standard, we know the number of mole, we put it in, we fill it up a bit of the way, dissolve it all, fill it up the rest of the way until the bottom of the meniscus is sitting on the line. Okay, and then we figure out our accurate concentration using the simple formula C equals N over V. Okay, and so basically this area here, this criteria for the primary standard ensures that N is accurate. Okay, and the way in which we fill up the flask ensures that V is accurate. And if N and V are both very accurate, then the concentration is very accurate and we have a standard solution. Okay, and that going back to this point where if we dissolve it, once we've already filled it to the line, if we dissolve the substance, and if that may cause the solution to go over the line, what that means is that if we go over the line, okay, assuming there's uniform concentration throughout, then yeah, we may choose to tip some out to get it back to the line. However, if we do that, then we've changed the number of mole. Okay, by tipping some of the solution out, we've changed the number of mole in the flask, so this concentration will be wrong. Okay, and that's why we can't overfill the volumetric flask when we're creating a primary standard solution.